Hello and welcome to another episode of Nathan Builds Robots. Today, we're going to be playing with a new filament. I don't know if any of you have heard of PEBA before, but it's the latest filament that Cinematron decided to send out to me. They've sponsored this episode, so I can tell you all about this really cool material. Now, when I say I'm going to be playing with PEBA, I mean that literally. Well, I'm no ukulele superstar, but this is one of the few filaments that's tough enough to be able to stretch and have all the required elasticity to make it as a stringed instrument string. This is pulled under high tension. I just took the basic filament, this PEBA filament right here, pulled it to reduce its diameter, and you can just see how tough this material is. Instead of breaking like most material would at this kind of tension, it just stretches out, it elongates quite a bit, and it's super strong. I'm going to try and see if I can pull this apart. It's pretty strong and kind of scary. I actually pulled one of these and let go of it, and it whipped back and snapped my finger, and it hurt quite a bit. So you got to be careful with materials that can store that much energy. I've been printing with it. I've printed tons of stuff using this Core 1 here. But what's this material most similar to? It's pretty close in behavior to TPU, but there's one huge difference. TPU is a very dampening material, as in when you drop it, it doesn't bounce very much. But this Cinematron stuff, this PEBA, is super bouncy. So you can see when you drop it, it bounces quite a bit. And that's what makes it ideal for materials where you need that spring back, whether that's a basketball or some kind of wheel where you want it to return some of the energy when it impacts something, or if you want to make something like a stringed instrument. This material would be ideal for that because instead of absorbing all that energy and deadening the sound, it just oscillates. But it's also super tough and it doesn't want to break. So as you can see here, I'm just going to go ahead and pull this until it snaps. Now this might hurt a little bit, so I'm donating my body to science for just a moment here. Ooh, it's cutting into my hands. Ooh, ouch. Look what it's done to my hands. That stuff has super high tensile strength. So it just reduces in diameter until it's a super thin wire, essentially. And you can hear, I'll put it right up next to the mic. Starts, sounding like a stringed instrument. And that's what gave me the idea to head down to my guitar center and pick up the cheapest ukulele I could find and just string it up and see if it plays. And it turns out you can tension these all the way up. You can tension these all the way up to standard ukulele tuning, which is super impressive because normally you use high-strength nylon. I'm super impressed with the filament because it can survive that kind of abuse, but also that strength carries over to the parts that you manufacture with it. So this was a failed print. It failed because I just didn't support it enough. This object was just barely clinging on to the build surface with a tiny amount of surface area here. And this stuff, you can't break it, even across the layer lines. Like, I'm really trying here. Compare that to this TPU. Well, the TPU is generally pretty tough as well, but I can get it to break along the layer lines. On the other hand, this PEBA stuff is just insanely strong. Let me take some pliers and really yank on it, and I bet I can get it to break here. This stuff is scary strong. All right, let me try one more time. I'm going to pinch it and twist it, and there we go. I finally got it to break along the layer lines. So this material is super tough, and the way I describe this stuff is it's like a super duper engineering material for dummies. If you want to use engineering materials like nylon that's reinforced with carbon fiber, I know that's all the craze with all the people who want to make super strong parts these days. But the truth is, I know most of you aren't structural engineers, and I know you're not going to design parts that are going to be actually strong with that stuff. The reason most things break is because you design little stress concentrations into your parts, and when you have a super stiff material and you load it up, as that material starts to deform, those stress concentrations end up just snapping. The material acts really brittle. But with stuff like this, if you design a weak point into your part, it's just going to flex and absorb that stress and distribute the strain more equally throughout your part. and it's going to end up a lot stronger 90% of the time, unless you're a super experienced structural engineer, which again, I'd like to see you guys post your credentials down in the comments. That's kind of a niche career path. I actually printed out a basketball here. I know that's all the craze these days. You know, everybody wants to get a 3D printer and print one of those viral basketballs. So let me just go ahead and grab this. Now, it isn't that easy to remove the support material. I actually pulled this off earlier. So that is one of the challenges of this material. But as you can see, this material is super bouncy. And you can make a basketball out of it. Now let me clear off a little patch on my desk so we can properly bounce it. This material does bounce like a traditional basketball. I learned a little bit of how a ball works. You'd think a bouncy ball is a super simple challenge to be able to analyze it and understand it. But something I found out is that with low intensity, oh, hold on, let me get that noisy ukulele out of here. If you bounce something from like a normal distance, it bounces like a typical ball, as you'd expect. But once you start bouncing it a little higher, did you hear that? It just transitioned over into making a super loud snapping noise. We'll do it a couple more times. Did you hear that? It was just a small increase in the amount of force I was throwing it with, but it starts, you know, making a super loud snap. And I think what's happening there is you may have played with a toy where you turn it inside out and it's like an inverted cup, and eventually it just springs down and goes whap, and it launches the thing up into the air. Well, I think with this type of basketball, it deforms elastically and pretty much like you'd expect at normal impact speeds. But once you get above a critical speed, what actually ends up happening is the ball inverts into a stable state where it's like an inverted cup, and then the energy is stored for a millisecond, and then as it's returning back to its normal shape, it goes snap, and it pops down and it hits the ground. So again, I'm going to donate my body to science here. We can feel it. You know, it just kind of harmlessly bounces off of my hand. Even when I throw it a little bit harder, it's pretty harmless. But once I get to that critical snapping speed, oh, didn't quite hit it. Let me get the ball. But once I get above that critical snapping speed, once I get above that critical snapping speed, can't quite get it. But I did this earlier where I threw it at my hand and it made that snap. It slapped my hand super hard and it stung quite a bit. So yeah, there's some interesting non-pressurized ball dynamics that I'd like to look into a little bit more one of these days. But let's take a minute to look a little closer at some of these test prints. So this was a mallet. Basically, I've got a hard side and a soft side. The hard side is 95% infill. The soft side is something like 30%. So it's a little bit squishier on that soft side than the hard side. And you can see the mallet bounces quite a bit. If we switch over to our TPU mallet, let's see how this one bounces. It doesn't bounce quite as much as the PEBA one. You know, that one's super bouncy. And then let's take a look at our TPU wheel versus our PEBA wheel. Our PEBA wheel, it's super bouncy. Our TPU wheel, it bounces as well. I'll just drop it. Versus the PEBA wheel. I mean, this PEBA wheel, you can tell it's a lot more energetic when I just drop both of these at the same time. Yeah, the PEBA wheel just keeps flying off. It's kind of hard to assess this over camera, but you gotta trust me, this PEBA is quite a bit bouncier. All right, and here's another test print that I did. This is some kind of duster, so you can blow air with this. You can see it's super tough and airtight. And if I plug the end here, you can see this is holding quite a bit of pressure. So this material's toughness really shines in a situation like this. Like I'm squeezing this as pretty much as hard as I can, and it's holding up quite well. Compare that to the TPU version. Now again, I printed this on a different printer, but it just didn't end up very good. This isn't a fair comparison because this print didn't quite turn out the way I expected it to. This one I printed on the Core 1, which is a really high quality printer, that Prusa Core 1. This one I printed on my Creality K2 Max, and I think I'd need to do a little bit of tuning to get this to work reliably. But you can see it does hold up pretty well and holds the pressure. This one turned out quite a bit nicer. I'm trying to flex it and break it. It's super strong. Then here's a solid PEBA version of that. And this one is super duper resilient. These are kind of interesting. This is a compliant mechanism, so you can print out this little pliers and grab things with it. It's a pretty neat print. You can even flex it open like this and grab the hammer and start hammering things. And I got this super big version of it as well, so I can pick up the pliers with the pliers and do some weird stuff. Here's another example of how PEBA and TPU are different. This is a TPU little wiggly worm that I printed out. You can see it does wiggle a little bit, but here's the PEBA version of it. You can see that wiggling is quite a bit more intense. It's super wiggly, made out of PEBA. And this is a 90A durometer versus a 92A durometer. So these are pretty comparable materials. It's just the PEBA is a lot more bouncy. Now, another difference between PEBA and TPU is that PEBA melts at a higher temperature. So PEBA's temperature resistance is more similar to ABS. It prints at about 250 to 260 degrees Celsius. Compare that to TPU, which prints at about 210 to 220 degrees Celsius. And that makes a big difference when you're talking about parts that will be exposed to elevated temperatures. So TPU is more similar to PLA in terms of its temperature resistance, and PEBA is more similar to ABS. And I think that temperature resistance also helps when you're printing it. Because this PEBA is printed at a much higher temperature, it tends to melt and bond super well to the previous layer. Versus the TPU, it's printing at a lower temperature, so the thermal energy of the deposited plastic isn't quite enough to superheat up that lower level and bond to it really strongly. PEBA, on the other hand, it's almost as strong in its interlayer bonding as it is in the normal bonding direction, so that's super cool. And if you really want to get into the material science of it, one of the things that makes this material super strong is the fact that it's so flexible. When you print a part and you have these little layer lines, they look like little ridges. Essentially, those little zigzags right at the surface of the part act as tiny little stress concentrators and little places for cracks to form and cause your part to completely fail. With PEBA, because it's so flexible, when you pull on it, those little serrations end up straightening out a little bit, and that material right in the crevice of those layer lines would normally kind of fail and have the crack shoot straight through the part and separate at a layer line. With this PEBA, since it's so flexible and it elongates so much when you pull on it, just look at this, whoop, it'll just stretch and form a new happy state and not end up failing. So you end up with super tough parts. Now, there are some downsides to PEBA which you can mitigate, but you should be aware of them. One of them is that support material is a little bit harder to remove. Because that material is so tough, it really doesn't want to break at the support interface. On this ball, it did a pretty good job of separating from the part, but it was a lot more difficult than what you would get with an ABS or a PLA part. And also, it sticks to the print bed super well. In one sense, the prints are super reliable because, just look at this bed adhesion. It's super strong. And you can see it just kind of peels away almost like tape. So it's pretty easy to clean up as well. But the downside of that is for some parts, I had issues peeling it away from the print bed. This one had a lot of surface area touching the bed. So when I peeled it up, it actually kind of caused it to plastically deform. So it ended up a little misshapen, but it works well. This is an example of a living hinge, and that's another great use of a material like this, where you just have the flexibility of your material act as the hinge, and you can get little closable containers like this. All right, so those are kind of the only downsides. The other upside of this material, which I can't evaluate right now, we have cold winters here in the Midwest, so I'll be able to properly test this out in a couple of months. But apparently this PEBA stuff retains its flexibility down to -40 degrees. Now that's -40 Celsius or Fahrenheit. One of the issues you have with a material like TPU is that If it gets super cold, it will become kind of hard and brittle and will be prone to failure. That's not the case with this PEBA. It can survive super low temperatures as well as elevated temperatures compared to TPU. The other downside is that you have to print this material kind of slow. Compared to a really rigid material, you can just shove it into the hot end with a lot of force using the extruder teeth. With this material, since it's so flexible, when you try to push it through the hot end, if you're pushing too hard, it'll just kind of collapse and cause some kind of issues. So as long as you're printing slowly or using a high flow nozzle, you'll mitigate that risk. There's some things you can do to avoid those issues, like have a well-ventilated printer. In the case of this Core 1, it exhausts a ton of air and helps keep the print area relatively cool, so that helps out. You might even be interested in getting a refrigerated hot end or something like that. Maybe you could liquid cool your hot end to below ambient temperature. That about sums up my experience with this PEBA. I think it's a super interesting material, and it's a more appropriate material when you want to make something super strong that won't break. If you want to make something that has high rebound energy and can take quite a beating, then this PEBA stuff might be the right choice for your next engineering application. So once again, thank you to Cinematron for sponsoring this video. Give me an opportunity to just spend a lot of time printing with this stuff and trying it out and seeing what it's good for. And I think this material has a lot more of a right to be called an engineering material. I'm going to call it the engineering material for dummies, because you can design your parts like a dummy. You can expect it to do all sorts of weird stuff like be super strong or super bouncy or flexible, and it just unlocks a lot of creative possibilities with your 3D printer. In terms of what I would want to improve with my printing setup to get this to work better, I'd probably be interested in switching over to a larger diameter nozzle so I can push this with a little bit higher flow rates and get my prints to complete faster. And I'd be interested in getting a multi-material printer, something like a Toolchanger, either a Prusa XL or that fancy new Snapmaker printer, the U1, that's a lower budget Toolchanger. That would allow you to print your support material in PLA and then print your PEBA on top of it. So, that could be pretty interesting to do, because then you could get more detailed parts and not have to worry about your overhang details coming out kind of scraggly. So that sums up my experimentation with PEBA for now. I want to do some more stuff with this material because it's really cool. I think someone like the Slingshot channel would like this stuff because of how stretchy it is and how it can just really whip back into shape. In terms of the actual material, apparently this is closely related to nylon, or maybe it is a type of nylon that's just treated with some additives. So it's got that super strength and flexibility of nylon, but it's even more stretchy and flexible than your standard nylon. So yeah, this is just really fun material. Oh, I got it to snap. There we go. All right, let me try that again. But anyways, I hope you guys had some fun learning about this new material. Thanks again to Cinematron for sending this material over for me to try out. And I'll put some links to this material if you want to pick some up yourself. I think it's a much better engineering material for the average person than carbon fiber nylon or these ultra high tensile strength carbon fiber reinforced filaments, which end up embedding a bunch of carbon fibers into your hands if you're playing with the parts too much. So maybe we'll revisit this material when I get a little better at playing ukulele, or when I can get a multi-material printer on the channel and tackle some more complex projects with it. Once again, thanks for watching, guys. I'll see you in the next video. And if you enjoy my content, consider supporting me on Patreon. That really helps out the channel and helps me keep coming out with these awesome videos for you all. One last thing, you might want to get a heated dry box like this. In this case, I've been using this Creality Space Pi X4. It can heat up these filaments and dry them out, because as a material that's related to nylon, it does tend to absorb moisture in the air, and that can ruin your print quality. So just make sure you're keeping it dry and your prints should come out just fine. That, and make sure to use a good, reliable printer like one of these Core 1s or a similar direct drive enclosed printer that's just going to give you better results overall in the long run. You definitely want to have a reliable printer when you're printing stuff like this, because it does flow relatively slow. So if you've got a 5-day print or something, let's say you're printing out a basketball and you want to make sure it doesn't completely fail on the 5th day of printing, get something reliable that you can trust. All right, that's it, and thank you for watching. We'll see you in the next one. Oh yeah, one last note, this PEBA stuff is used in industries like footwear. For example, Nike is using PEBA in some of their ultra high performance running shoes. That rebound helps runners regenerate more of their energy when they take a step, and it bounces them up and makes them travel a little bit faster. So PEBA is a well-known material in the footwear industry. They actually tend to use a version of foamed PEBA, and they're probably not 3D printing it, but maybe they're prototyping some stuff using an FDM PEBA blend like this. So yeah, get your hands on some of this using my link in the description below. Thanks again to Cinebatron, and I'll see you in the next video. Until next time, this has been Nathan Builds Robots, and we're signing out.